In this particular context of this topic, I'm aware that I'm probably talking to you about things that you already understand well. You are teaching in Queensland, you have been teaching in Queensland. I haven't been teaching in Queensland. I have been teaching in other states around the country and in other countries around the world. So what I'm going to try and share is a few overarching principles and ideas. Things that are helpful in planning that will enhance what you're already doing, and maybe just look a little bit at the differences between planning for senior secondary and junior secondary science. We sometimes think that a detailed written plan is going to stifle our creativity, that we'll be stuck and locked in and so on. I think it's actually the reverse, and you may well know this already, that if you've got your plan laid down, then you can always diverge because you know you've got it to come back to. You can avoid the problem that my year 7 science teacher fell into, which is that we could ask him for stories and he would tell stories all day and teach us no science, which we enjoyed but wasn't really effective for our science education. But basically having the plan in place means you can move the blocks, and when there's a sudden storm or a lockdown or a sports day that you hadn't been told about and have suddenly discovered, or a new public holiday or whatever it happens to be, you can easily move the pieces around if you've got the pieces there captured. But it's harder if you're trying to remember where you are up to and what you're doing. If somebody comes in to cover for you when you're sick or off for whatever reason, obviously a detailed plan is helpful. The amount of writing that you're required to do obviously gets less as you're more experienced because you're just making notes for yourself. But at the same time, as I just said, someone else may have to interpret it if, heaven forfend, something happens to you. So making it explicit enough that another experienced teacher at least can read it and understand it, I think is really quite helpful and important as well. And you're required to, it's mandated. You'll be required to show your program of work to people. You're already doing all of this. So I'm probably preaching to the converted on this particular point. In physics education, obviously we need to also book in materials, talk to the lab tech, borrow materials to take for a demonstration in the classroom, set things up, pull things down, make sure that we have web access if we want to show students a visualization on the web. There's a whole variety of things that we require to set up ahead of time. I talked about what assessment under the new syllabus that's forthcoming will be like, and the fact that you will have to create your assessment tasks and send them off for moderation by somebody else where. So again, you'll be setting up your assessment tasks and planning them well in advance, and your planning definitely helps with that. It also allows you to implement the curricular emphases approach, which I'm going to talk about in a minute. One difference between junior secondary and senior secondary science planning is that you are planning for 2 years in senior. In junior, you're just planning for the 1 year for year 7, 8 or 9. In senior, it really is quite designed. We've talked about the fact that it gets less scaffolded, more independent for students in year 12. They're expected to do more and do it more deeply. So there really is a plan about how their knowledge and skills and attitudes develop across the 2 years. And so planning that in advance, even if you're not going to be the person who teaches them for the whole 2 years, they may well go to somebody else depending on the circumstances. But if you've kind of laid the groundwork and you've got a plan that you can pass on and say, this is what they've done, this is what they know, this is what they can do, this is what they still need to develop, and so on, that obviously helps as well. I said that the units should have a storyline. It doesn't necessarily mean a narrative, but what it means is a story sets up expectations at the beginning, complicates them in the middle, and resolves them at the end. So the first chapter of a good novel will create a problem for the protagonist, and whether that's a conflict with an antagonist or whatever that happens to be, it will create some kind of problem that the person needs to solve. Is it a murder mystery where they need to solve a murder? Is it a romance where their eyes meet across a crowded room and they want to get with this person? Then the middle complicates factors. New witnesses come in, new clues arise in the murder mystery, somebody misunderstands something in the romantic novel, and the middle complicates and gets in the way of the resolution. And then at the end, the situation's resolved. We know who the murderer is, or the couple is together and lives happily ever after, or whatever it happens to be. You see what I'm saying? That a unit should be like that as well. A unit should, at the beginning, set up expectations on the part of students. What are we going to learn? What will we understand at the end of this unit that we don't understand now? How will we understand the world better once we've studied this? The middle complicates it, makes it richer, deeper. They engage with it, work with it, add complexities, add details, and so on. And the end, in some way, should satisfy. So it shouldn't be just, okay, it's the unit's been 6 weeks, now we do the exam, now it's the next unit, with no ceremony. There should be some kind of, hey students, have a look. You didn't know this 6 weeks ago. Now you do know it quite deeply. You can understand the world in new ways. That storyline is one of the things that really helps with student engagement. It helps them understand what they're doing and do it meaningfully. They're not just doing the lab because you've told them to. They're doing it because they understand that they're trying to develop and test a particular concept, or test a particular knowledge claim, or distinguish between two competing knowledge claims. So it makes the learning meaningful for them. Curricular emphasis approach I owe to a colleague of mine from Canada. His name is Frank Jenkins. He's well into his 70s now. He taught chemistry for 65 years in Edmonton, Canada. And then he retired and did a PhD and became a teacher educator. So he worked with me when he was quite late in his career and I was very early in my career when I was in Canada. And he developed this model based on some of the science, technology and society work that others like Glenn Aikenhead had done. And I think it's quite nice. So when we teach science, we have these other interests about connecting the science to the real world in some way. We want students to develop an understanding of the nature of science and what does it mean to make and support a knowledge claim. How can we test if somebody tries to sell us a little box that you wire into the ignition of your car that they claim will make it more efficient and more environmentally friendly? How do we test that knowledge claim? How do we test that claim that's being made with evidence? Is there a way that we can find that out? So you want students to understand the nature of science. You want them to understand technology, the links between science and technology, the ways in which technology advances science sometimes, science advances technology other times. For example, brewing is one of my favorite technologies. We knew how to make beer. The Egyptians were feeding it to the slaves who were building the pyramids. So it's a very old technology, but until we really understood the microscopic world of yeast and fermentation, science hadn't caught up with the technology of brewing. We knew how to do it, we just didn't know why it happened. Some of Einstein's science around general relativity, which we'll be discussing in this module as well, was developed in about 1915 and couldn't be really properly tested until quite recently, well, the 60s and 70s, when we had fast planes that could fly high and atomic clocks that were very precise, so that we could actually test his predictions. So science could make the prediction, but technology had to grow for another 4 or 5 decades to be able to test the predictions. So the relationship between science and technology is something that we in physics want to be able to talk about. And the relationship between science and society, talking about energy and our forms of energy, should we use nuclear as part of the mix of energy? 30 years ago we would have said no because of the problems with nuclear waste and so on. Now we know with the problems about the problems of fossil fuel waste, which is greenhouse gases. So do we have to rethink it? Can we use solar, wind, hydro, tide, etc., so that we don't have to use nuclear? Right? This is a socio-scientific question. There's no single one right answer. It's not a scientific question. It's a social question. And people can argue quite persuasively and quite accurately for a number of different perspectives. We want students to be able to do those things. We're looking at their attitudes and values and developing those. So how do they make these judgments? They're doing the evaluating and concluding as an exit criterion. They have to be able to make judgments and make conclusions. But if we had to do all 3 of these things in every unit all the time, it gets to be very demanding. We're trying to do all of the content, trying to develop the skills, we're trying to develop the attitudes and values, and we're also trying to do these emphases. And Frank's innovation was the idea of, well, you might have, I said 5 to 8 units in a year. You might do, therefore, 10 to 16 units across the 2 years, call it a dozen. And in that time, there'll be some units that will fit quite neatly with a nature of science emphasis. They'll be of the kind where talking about the nature of science fits neatly, and it isn't extra work. It isn't some add-on that you're adding. It's integral to the unit, but it's an emphasis. This is why it's called curricular emphases. So for those, say, 4 units out of your 12, you'll give it a nature of science emphasis. And when you're planning the unit, you'll just think about, well, where are the opportunities to sneak in a little bit on the nature of science? How can we make sure that students are thinking about what does it mean to do science? How do we tell science from pseudoscience? How do we tell science from scientism? The belief that scientific knowledge is the only science that matters, or the only knowledge that matters, sorry. And all of that kind of stuff. And another 3 or 4 or 5 of the units might have a technology focus. So maybe the electricity one, you might focus on why high tension lines are 110,000 volts. And there are good scientific reasons for that, but there's a particular technology there as well. Or you might look at superconductors, which we've also talked about, or a whole variety of other technologies. So that unit would be given a technology emphasis or a science and society emphasis. So I really like this model because it means we attend to these 3 things that are really important without it taking over all of our time or eating into our ability to do things. But it makes your physics course richer, better, more effective, more engaging, prepares students as citizens, not just as future scientists. Planning, I think I've already said this, but continues to change all the time because new things come up. You see a program on TV that has some new topical idea and think, hey, that would fit really well. You see a video on YouTube or a simulation or something online and think, hey, that would be great. Or this class is not so bright, or is extra bright, or is not so engaged, or is extra engaged, or is interested in something specific. So there's a whole variety of ways in which circumstances can change what's happening in a unit. The syllabus tends to change. As I think I might have already said, we've been very lucky in Queensland that we've had the same syllabus for 9 years, but that's about to change. So that clearly will change the planning that we have to do. Planning is always it's never finished. It's an ongoing dynamic process. Making good notes this year of the things that you want to change for next year is also an important skill, and then knowing where to find those notes. That's pretty much it for planning for teaching. And as I say, hopefully kind of principles that you can apply to your existing knowledge around planning. The optional assessment task, for those who do in this course want to complete the optional task for university credit, it'll be equivalent to 1 course worth of credit towards probably the graduate certificate in STEM education that we're preparing at the moment, although breaking news as of yesterday, it might be called the graduate certificate in STEAM education instead. But whatever it's called, or there's a graduate certificate in professional learning as well that we're in the process of developing. You will be able to get credit for 1 course towards those graduate certificates, which consist of 4 courses. So you would have 3 further courses to finish. If you want to do that, then the task is have a look. There is a link on the left-hand side of the Learning at Griffith page for this program called Optional Assessment. If you click on that, you'll see a program of work there. The program of work is for physics. It's from a Queensland school. I've de-identified it, so you don't know which school, but it's from a real authentic Queensland school, and it's a real authentic program of work. And your mission is to take everything you've learned in these modules, both the content knowledge and the knowledge about the syllabus, about planning, about EEIs, about teaching in context, about balance, about the structure and the order of topics, all of that stuff. Evaluate what that school has done. Because I think it's pretty good, I think it's decent, but nothing's perfect. And planning's always dynamic. And your context is different, right? There's something different about your students than this school's students. So evaluate what they've done, write a discussion of what they've done, and then here's how I would improve it. This is how I would change this program of work for myself. The assignment itself is around about 2,500 words, although I don't care specifically about words. The reason we put a word limit in is you're not going to be able to do that satisfactorily in 500 words. if you do 10,000 words, you're going to kill yourself for no real benefit. So 2,500 words is a guideline, not a rule. I know some of my colleagues say the word limit plus or minus 10%. No, I'm not going there. But do write it, if you do it, write it like a university assessment, use proper referencing and so on, make it high quality presentation, all of that good stuff. The criteria sheet for that assessment is up on the website as well. But it is basically a pass-fail task. It's not a task that we're grading. So you need to demonstrate your knowledge of the physics content and the syllabus stuff, all of those bits and pieces I just mentioned, in completing that assessment. If you're not going to complete the optional assessment, and that's entirely your right, if you're going to get enough out of the modules themselves to make you feel confident teaching and you'll get the certificate of completion, I'd encourage you to still click on that link and just look at the program of work. I think there's value there for you in just having a look at what does the thing look like, how does it differ from the ones you're already doing in junior secondary, where are the EEIs, where are the ERTs, where are the essays, what's the total mix of assessment tasks, where are the contextualized units and what are they, and so on. So it makes sense to have a look at that, just so you know a bit more about planning for teaching in physics.